Okay, we now get on to probably the first thing that people think of once they've studied materials, and that's Hooke's law. And this is so named after Robert Hooke. I've got a separate video on him elsewhere, and this is looking at how objects extend. I mean, it is compression as well, but normally we're looking at things that are extending, and how the extension is related to the applied force, which Hooke showed, at least within the elastic limit, that they're proportional to each other. So if we were going to draw a graph of force and extension, and I'll get on to why we got force on the y-axis in a moment, because you could put it either way round. I mean, we got a straight line through the origin here, so the two are, we got no force, we got no extension, and then they increase linearly like that. Within the elastic limit, that's the thing that's really important. So as you're applying the force, the object will stretch out to we're going to have some maximum here, which is going to be the elastic limit. Up until that point, if you then release the force, it will then go back down the same line. So we will extend out and then we'll compress back down again. So yeah, we've got that relationship. This is an empirical relationship that Hooke discovered, back in the 17th century. So this is all, all fine and dandy. We've got our F is proportional to extension. So we'll put in our constant of proportionality K, which is the force constant. And the force constant, we can see that's in newtons per meter. And this is really why we've got the axes this way round. I mean, when you get these relationships, these empirical relationships, we're used to putting the control variable on the x-axis, and it depends what you're doing when you're actually conducting the experiment for this. Are you extending an object? Like, say you had a spring hanging down and you were thinking, well, let's attach this to some force meter, we'll pull it downwards, and then every centimeter maybe of extension we will measure what the force is. So that's one thing that you could do, in which case the extension is your x-axis. You could say, well, let's keep varying the force and measure what the extension is, in which case there'd be the other way round. So it doesn't really, we haven't got any great preference for which one of the variables is put on the x-axis, but it gets cemented in because we put the force constant on this side of the equation here, and we're expressing this force constant in newtons per meter. So you have to come down on one side or the other. We could have put a constant on the other side and then add meters per newton, but that's not what's happened. So historically, this is what we've got, this is what we work with, and we've now got it in this y equals mx format, so we put the force on the y-axis. Like I say, this works for extension or compression. Mostly we're going to be looking at extension on it though, but you can still have the elastic region for both, for tensile forces and compressive forces. So that's fine. Let's have a quick look at what's going on with this K then. So if we've got a high force constant, then that is a lot of newtons per meter of extension. So a high K means we've got a stiff or rigid object. If we've got a low K, then we've got something which is very stretchy, because we don't need very many newtons for each meter. So newtons per meter. So newtons for each meter of extension, or centimeter, or whatever unit force per unit length we've got here. So yeah, this is what's going on with Hooke's law. Is relatively straightforward then to to solve problems using this. It does bring us into then okay, springs. I mean, I've mentioned a spring here. We work a lot with springs because metal doesn't stretch very much. If you've just got a straight bit of metal, a metal wire, then you're going to have a pretty high force constant. K is going to be a large number, is not going to stretch very much. It might be quite brittle, as in you're not going to get much extension before it snaps. Put it into spring form, and now we can get much more extension for the same amount of force because we're bending the object in a different way. We're just getting a little for every coil of the spring, we can just have a little angle deformation. We can increase the angle of the spring as we load it, and then you're going to get a much bigger increase in length for the same force. So that's why we're using springs in a lot of cases, just because we can't stretch metal otherwise very easily. So yeah, it's just a nice way of extending the materials that we can apply Hooke's law to. So each spring then is going to have a different force constant based on really the geometry of the spring, as well as just the material that it's made of. Are they big loops, little loops, these sort of things. So how thin is the wire? So the force constant is going to be highly variable for these springs, and we can work the same material into different shapes in order to get very different response. You're going to get stiff springs, stretchy springs. I keep saying string instead of spring, but you know what I mean. So depending on how thick is the wire, how tightly we coiling it, things like that. So springs in themselves, there's a lot that can be done on that. If you look at the springs that you get maybe on the suspension of a car, they're pretty substantial things compared to something you might get inside a I don't know, propelling pencil or biro or something like that. So yeah, there's a lot can be done with those. Right, okay, final thing then is energy. If we've got this plot here, so we're dealing with forces and distances, so that's immediately make us think of work done. We've got this force times the distance is the work done. So that is going to be work that is going to go into the elastic potential energy, usually shortened to EPE, in the spring. So if we've extended a spring by putting a load on it, then this spring is going to be holding some potential energy. It's going to be a store of potential energy. And that would have come from the drop in, say, gravitational potential energy of the load, which would have dropped through a height, and that change in gravitational potential energy in the load has now moved into elastic potential energy in the spring or the rubber band or whatever it is that we're hanging it on. It's still going to be elastic potential energy. So we want to look at the work done, which is the average force times the distance. Average force times distance. So looking at this graph, we can think of that different ways. We can either say, okay, well, we've got this. That's our average force. You're going through the middle. We're starting at 0, so average force is going to be F over 2. Multiply that by X. That's giving us that area, which of course is the same as the area of this triangle, because this is a half base times height. So the area under the graph on a force extension graph, that area underneath the line, that is our work done. That is our elastic potential energy. So we're looking at a half EPE is a half F times X, and we know that F of course is KX, so that is a half KX squared. So we've got two ways of putting that together. So if we've got a particular force constant and we know our force constant for a material or a spring, whatever the setup might be, then we just need to look at the force constant and the square of the extension, and we're going to know what the energy is that's stored inside that stretched or compressed material, because compressed materials can spring back in the same way as stretch materials can. So yeah, we've got these two key equations that we're going to be using a lot. We've got the force is equal to K times the extension, and we've got the elastic potential energy is a half Fx, which is equal to half Kx squared. And we're going to be using those loads in our calculations from now on.